The third confirmed interstellar object is racing toward our solar system at 130,000 miles per hour. On paper, 3I/Atlas should be just an oversized comet, but its path arcs past Mars, Earth, Venus, and Jupiter in precise, rapid sequence, a route with less than a 0.005% chance of happening by pure coincidence. Its immense size, unexplained acceleration, and uncanny four-planet flyby have top scientists whispering, is 3I/Atlas really a nuclear-powered reconnaissance craft here to test our response? If it's engineered, the stakes are off the charts. Humanity's first contact and our response plan may depend on what we discover next. But what evidence could finally prove what we're really dealing with? July 2025, the numbers begin to stack up. The object catalogued as 3I/Atlas cuts across the solar system at 130,000 miles per hour, fast enough to cross the Atlantic in less than 2 minutes. Its measured diameter, nearly 20 kilometers, makes it the largest interstellar visitor on record. For comparison, that's the length of Manhattan, moving with a velocity that dwarfs any known comet or asteroid. Astrometric teams at the Rubin Observatory and TESS sift through early detections, logging each position with millisecond precision. The orbit, reconstructed from dozens of images, reveals a hyperbolic path, unbound on a one-way trajectory through the solar system. But the fit isn't perfect. Residuals in the data suggest subtle deviations from the expected gravitational curve. Analysts debate the significance. Is this just noise from measurement errors, or the first hint of a force beyond gravity? Standard comet models predict some non-gravitational acceleration, jets of gas venting from sunlit ice, nudging the nucleus off course. Yet, for 3I/Atlas, the coma is faint and oddly positioned, with little evidence of classic outgassing. The photometric profile is even stranger. Its brightness holds steady, not flickering or fading as it rotates. No telltale spikes, no dips from tumbling or jet-driven surges. At this size and speed, any natural process should leave a signature: thermal recoil, volatile jets, solar heating. But the data show a near-mechanical consistency. Escape velocity calculations confirm what the orbit already hints. Unless something slows it down, 3I/Atlas will never be captured by the Sun. Its hyperbolic excess velocity, the speed it carries even after escaping the Sun's pull, is among the highest ever measured for a natural object. For some, the absence of a clear natural driver raises the question: could there be an engine at work, hidden beneath the coma? The search for a definitive answer pushes astronomers to probe deeper, dissecting every anomaly in the motion of this Manhattan-sized interloper. August 2025, the reconstructed orbit of 3I/Atlas draws a line through 4 planetary neighborhoods in less than 6 months. Mars, Earth, Venus, then Jupiter, each encounter plotted within a fraction of an astronomical unit. The sequence is not a simple brush past the Sun, but a multi-planet circuit, each flyby close enough for telescopes to capture detailed spectra, yet distant enough to avoid gravitational capture or catastrophic disruption. Orbital simulations run at the Rubin Observatory and by independent teams reproduce the tour with thousands of virtual clones. Even after accounting for measurement errors and possible outgassing, the alignment holds. For nearly every plausible version of the orbit, the object's path threads the needle, skimming the orbital lanes of Mars and Earth, swinging inside Venus's orbit, then slingshotting toward Jupiter. The geometry is not just rare, it's an outlier among outliers. Galactic models built on random ejection and capture predict that less than 1 in 10,000 interstellar objects would stumble into such a chain of close planetary approaches by chance. Avi Loeb's group publishes a striking figure: less than 0.005% probability for a random visitor to match this 4-planet flyby pattern. The claim circulates through Telegram groups, preprint servers, and conference hallways. Critics push back, pointing to survey bias. Discoveries skew toward objects that pass near the ecliptic, where telescopes sweep most often. But even after correcting for these biases, the odds remain punishingly low. The tour's choreography raises new questions. Is this a reconnaissance sweep, maximizing vantage points while minimizing risk? Each planet offers a unique window on the solar system, and the timing, Mars, then Earth, then Venus, then Jupiter, favors observation without lingering in any gravitational well. The object's path hints at intent, or at least at a pattern that natural processes struggle to explain. For planetary scientists, the debate moves from physical anomaly to the possibility of purpose. The next question: if this is reconnaissance, what comes after observation? Avi Loeb, the Harvard astrophysicist who once put Oumuamua at the center of an alien probe debate, steps into the 3I/Atlas controversy with a new warning. For Loeb, the choreography of the object's path, threading Mars, Earth, Venus, and Jupiter, is not just a mathematical fluke, but a sign of possible reconnaissance. He points to the odds, less than 1 in 20,000 by his calculation, for a random interstellar visitor to pull off such a tour. The figure circulates in research preprints and late-night podcasts, fueling speculation that 3I/Atlas is not simply wandering, but watching. The pattern echoes a scenario from science fiction, the dark forest hypothesis. In this universe, every civilization is a potential threat, forced to stay hidden or risk destruction. If 3I/Atlas is a probe, the logic runs. It would scan the solar system from a distance, sampling planets while never straying close enough to be intercepted or trapped. The flybys maximize coverage, minimize exposure, and avoid the gravitational wells that would slow or capture a careless visitor. Each approach is brief, each window for observation fleeting, as if the object is collecting data and moving on before anyone can react. Loeb's group draws parallels to Oumuamua's mysterious 2017 flyby, suggesting that if that object was a scout, 3I/Atlas could be a follow-up, a larger, more deliberate mission. The timing, 8 years apart, fits a programmatic cadence. Critics counter that the theory leans too heavily on coincidence and underestimates the power of selection bias. Still, the debate sharpens. Is this a peaceful survey, a test of human detection, or something more dangerous? The question lingers, unresolved, as astronomers weigh the risks of being seen in a universe where silence may be safer than curiosity. Dr. Rachel Stevenson, a planetary scientist at JPL, surveys the spectrum from 3I/ATLAS and finds a familiar pattern. The coma, though faint and oddly forward, contains water, carbon dioxide, and trace organics, hallmarks of a comet formed in the deep cold between stars. Hubble's images reveal a diffuse sunward haze, but no sharp jets or metallic glints. Reflectivity measurements match bright, icy grains rather than engineered alloys. For Stevenson and most of her colleagues, the simplest reading is a natural one: a comet, albeit a rare and oversized wanderer, not a vessel. Spectroscopy teams track the carbon dioxide to water ratio, 8:1, among the highest on record. This points to an origin far from any star, where carbon dioxide ice can survive the journey. Isotopic signatures, though still uncertain, fall within the wide scatter seen in solar system comets and Borisov, the last interstellar visitor. The coma's brightness, measured at multiple wavelengths, rises and falls with solar distance, not with any internal pulse. Each new dataset chips away at the extraordinary claims, grounding the debate in chemistry and physics. Yet the question of response remains. Project Lyra's engineers run simulations. To intercept 3I/ATLAS would demand a velocity change of at least 60 kilometers per second, a leap beyond current rockets. Light sail designs, inspired by breakthrough Starshot, might reach the target, but only with gram-scale payloads and years of pre-planning. ESA's Comet Interceptor waits at L2, ready to pounce on slower comets, but lacks the muscle for a chase this fast. For now, science must rely on telescopes, not probes. Policy advisors revisit the Outer Space Treaty's rules. No unilateral signals, no nuclear devices in space, all actions subject to international review. SETI and United Nations working groups debate whether to send a message or stay silent, weighing the risks of contact against the cost of inaction. The protocols are clear: observe, consult, prepare. As 3. I/ATLAS sweeps past, the world's response is shaped not just by what it is, but by how we choose to meet the unknown. Its 20-kilometer span, 130,000 mile/hour speed, and multi-planet flyby, passing Mars, Earth, Venus, and Jupiter within months, placed it among the rarest solar system visitors ever observed. Despite well-documented non-gravitational acceleration and a tour path with less than a 0.005% probability by chance, spectroscopic data from the JWST and ground-based telescopes detected a diffuse coma and high reflectivity, consistent with known comet behavior. What remains unknown? The true cause of 3I/Atlas's anomalous motion and whether similar objects will appear. With only months to observe, projects like ESA's Comet Interceptor and Project Lyra outline tested strategies for rapid response. Whether natural or engineered, 3I/Atlas challenges humanity to meet the unknown with science, preparation, and open data.